Yeah.
All right, let's run through these questions. So I know I normally grade one question, but I decided to grade one from each of the 4 sections because I don't think we're going to have any more homeworks. But you'll probably see combinatorics on your quiz Friday. So let's go through these. So section 2.1, which is basic product rule, pretty much, ways to do tasks. So I graded number 15. So 15 is a question where you're going out to dinner, and you have a choice of fish, lamb, or beef for a main course, peas or carrots for a vegetable, and pie, cake, or ice cream for dessert. And they want to know how many different dinners are possible. And I think everybody got that correct. The solution is just to multiply those. So break the task of choosing your dinner into 3 subtasks. Choose your, what do they call, their main course, your vegetable, and your dessert. And the number of ways to do the main dinner is 3, number of ways to do the vegetable is 2, dessert is 3. Multiply those out, that's 18. So when you do this on a test, right, I strongly recommend at least putting this down as opposed to just the number, because a lot of people make math errors, and if you write down 21 and I don't know how you got it, I can't give you any credit, right? If I see 3 times 2 times 3 equals 21, you'll probably get full credit, and I'll just tell you, to check your math. So whatever you're doing to get the answer, make sure you indicate that. Unless I ask for an explicit number, you're fine sometimes just leaving it like 3 times 2 times 3, especially if it's a big, long, hairy computation, 42 times 41, blah, 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 as long as it's clear that you know what we're trying to do. So most of these questions are the same thing, right? The one on basketball players I didn't grade because that one assumes you know basketball. So permutations, right? Permutations, do we care about the order or do we ignore the order?
Permutations, ignore. Care about order.
Care about the order. Combinations, we throw away the order, so combinations are smaller. So permutations look like this, right? And that's just a shorthand for the product rule, k n times n minus 1 times n minus 2. When you want to do combinations, we also throw an extra k factorial on the bottom. This is the number of ways we can arrange k things. So we're sort of modding that out from the number of permutations. So we're throwing away 1, 2, 3, 2, 3, 1, 3, 1, 2, 1, 3, 2, taking all of those and lumping them together. That's what the effect of dividing out by that factorial is. So this ignores order. Permutations pays attention to it. So 2.2, we're looking at permutations. So raffle has 3 different prizes. There's 1,000 tickets sold. Different prizes is key here. If there were 3 identical prizes, then the order in which we pick the 3 winners wouldn't make any difference, and it would become a combination question. In this case, the order matters, so it's just the number of 3 permutations of 1,000 objects. And like I say, unless I say, make sure you give me a number, this is fine for the answer, right? If you want to expand it, that's also fine for an answer. And if you want to write it out, it's some slightly disturbing number.
7002000.
Yeah, thank you. All right, this is the easiest to write and least likely to be wrong. But those are all equivalent. Okay, and these are all kind of the same. How many 8-letter words can you form from the 26 letters in the alphabet? It depends if we're allowing repeats or not. Right? If you're trying to form something from a set of objects, that kind of implies we're only taking one of each object. But in typical English, when we make a 8-letter word, it can have repeats, so that's why there's 2 interpretations of that, I think. But 8 letters, order matters, so number of 8 permutations of 26 objects, assuming you can not reuse. What is it if you can reuse?
Howard.
Yeah. So without reuse, number of ways we can pick 8 things from 26 objects. If you're allowed to reuse, you still have 8 subtasks, which is pick the first letter, second letter, third letter, but the way you can do each of those is 26, so this is actually 26 to the 8th. This is 26 times 25 times 24, it gets smaller.
The issue is that if your word is all the same number, it doesn't really make a difference if you rearrange it. You know, like if you go or whatever.
Oh, that's true, that's true.
If you rearrange it.
So, yes, so reuse allowed, this is different.
Good thing you've already graded.
Yeah, I didn't do this one because it always causes confusion. Yeah, so what is the answer there? I seem to remember we had a hard time with this last quarter.
That's what they're talking about, reuse. Or with repetition or something instead. Because you're going to get a whole bunch of repetition if you give all different permutations of the same thing.
Right. Yeah, so if you don't reuse, it's clearly number of 8 permutations. Right, because you only get 1 of each. But yeah, A, B, B, A, B, B. Yeah, so we need a weird language where the position of the letter changes its value. So I won't ask you that on the test. Did anybody get a good answer for that one, though? And I don't know if that's the second interpretation they're talking about, because we don't know. All right, so 2-3, we're talking about mostly principle of inclusion, exclusion. And I saw a few different answers for this. So the correct answer is 18, but the number of people got 17. And the numbers that I saw come out to 17, but I don't know what the process was. Let me show you how I'm thinking of it, and then we can talk about other ways that we might think about this. So we are looking at number 7. So let me write this down and I'll switch. So we have 90 people. We have 47 playing tennis. We have 42 swimming. And 17 in both. We want to know how many participated in neither. So here's one way to think about this. Let T equal the set of people who took tennis. And let S be the set of people who took swimming. So we're told the size of T is 47, and we're told the size of S is 17. And we're told that there's a total of 90 people being considered. So 17 people took both, so what does both mean? Yeah, so what does that mean in terms of T and S? The sets.
There's an interlap.
Yeah, so it's telling us that if we look at the intersection of S and T, why'd you let me write 17 there? 42 people swim. The overlap has 17 people. And so our rule for inclusion, exclusion says the size of the union is the sum of their sizes minus the size of the overlap. So this is 47 plus 42 minus 17, which is 72. And S union T, this is a set consisting of all the people who took either swimming or tennis. Right, so you take 90 people and you say, okay, if you took swimming or tennis, go stand over there. This is the set of people that will be standing over there. And anybody who's not standing over there took neither swimming nor tennis. So if you take the number of people in this and you subtract that from the total number of people, that gives you the number of people that that didn't take either swimming or tennis. So it's 90 minus 72 is 18. Or if you like, it's the complement of this union in the universe of people. And this is just a fancy way of saying 47 tennis, 42 swimming. That's a total of 89 people, but 17 of those people got counted twice. So subtract 17 from 89. And you get your 72 non-overlapping. Does that make sense?
So A will be people both.
Say again?
Number A will be people.
So 18 is people who did not take either swimming or tennis. So this is right, that's the size of the complement of the S union T. And I saw a lot of different solutions to this that all came up with 18. Saw one Venn diagram, which was cool, and lots of different ways of arguing through it. But that's one way to think about it. And most of these are the same thing, right? So, and you can do this with more than 2 sets. And you can look in the book to see the formula. But if you have 3 sets and you know what the intersection of each pair of them is, you can find the number of things in the union by adding up the size of each 3 and subtracting different combinations of the intersections. So when you got 3 phones, back when the world had 3 types of phones, you can do that with the same principle. I miss my BlackBerry. Blackberries were awesome. Just saying.
Didn't they make a new phone recently?
Yeah, but it's got a touch screen keypad, which was kind of cool, but just didn't have the BlackBerry feel to it for me. But it was cool because you could mouse on top of the keys. So 2.4. And we skipped over binomial theorem, and I think I'm okay with not going back to pick that up. But a lot of these questions are about binomial theorem. Yeah, I will go back and pick it up because I love the binomial theorem. But the triangle question was the one I graded, triangles and points in a plane. So you have 10 points in a plane and no 3 lie on the same line. How many lines are determined by the points? And the most straightforward way to do that, so here's a bunch of points and no 3 are collinear. We want to know how many lines we can draw. Well, what do you have to do to draw a line? You have to pick 2 points. Right, so here's 2 points, that gives us a line. Here's another 2 points, that gives us a line. Here's another 2 points, that gives us a line. Ooh, beautiful artwork. There's 2 points, that gives us a line. Here's 2 points, gives us a line. Here's another 2. Right, and anytime I pick 2 points that are different from each other, I get a line. So how many lines can I draw through these? How many ways can I pick 2 points? And the order of the points doesn't matter. If I pick this point and that point, I get the same line as if I pick that point and then this point. Right? So the order doesn't matter. So this is just 10 choose 2. number of two combinations of 10 objects. Yeah?
But can't you not pick the same points that you picked the first time?
What's the first time?
Well, when you want to make a line, you have to pick 2 points, right?
Right.
When you pick the first point, you can't pick the second point?
So I picked this as the first point. Second point has to be different.
Yeah.
Right? So, and when we do combinations, we're talking about picking two things we're not allowed to repeat.
Okay.
Right? So, if we allow repeats, then we go back to the product rule and wire it up. But combinations, permutations, we're rearranging things, right? So we're picking 2 points out of the 10. And so this turns out to be 10 times 9 over 2, which is 5 times 9, which is 45. And then triangle is exactly the same thing, except to pick a triangle, you have to choose 3 points. And so that's just 10 choose 3. So 10 times 9 times 8 over 3 factorial, which is 10 times 3 times 4, which is 120. Okay, let's talk about binomial theorem. So you know how to multiply polynomials, right? You've been doing this for a while. So let's imagine a friendly polynomial. Let's just start with x plus 1. And just for kicks, I'll do that x plus 1 to the 0, that's equal to 1, because anything raised to the 0 is 1. X plus 1 to the first, I'll do that one for you too, that's x plus 1. Okay, what about x plus 1 squared?
X squared plus 2x plus 1.
How did you get that, besides remembering it?
You can, yeah. So you
Yeah.
can expand it, you can change, or then you're foiling.
Yeah, you're foiling. So x plus 1 times x plus 1. So first we're going to take x plus 1 and multiply it by x. Then we're going to take x plus 1 and multiply by 1. And we're just going to add those together. Okay, so and there's your answer that you already had. Now suppose we don't know this answer ahead of time. Let's suppose we're doing x plus 1 cubed. And we don't really want to FOIL this. But we know our biggest power of x is going to be x cubed, right? So this is going to be something times x cubed plus something times x squared plus something times x plus something. When we multiply this, we're going to get out a bunch of individual terms that we're going to add together. Okay, we're going to multiply all the possible combinations. We're going to get a whole bunch of these things. We're going to add them together at the very end. Okay, bless you. Some of these may have an x cubed, some may have an x squared, some may have an x, some may have just a 1. Right, and we're going to write them all out, and then we're going to combine them. Okay, to get one individual term that I'm going to add, what I need to do is choose which one of these terms do I want to pick, which one of these terms do I want to pick, which one of these terms do I want to pick, and I'm going to multiply them together. So up here, for example, I might say, okay, I'm going to choose the first term here and the first term here. That gives me 2 x's. I multiply that. That's my x squared. And then I might say, okay, I'm going to take the second term here and the first term here. 1 times x, that's going to give me an x. And I'm going to take the first term here and the second term here. That's going to give me an x, and I'll take the second term and second term. That gives me 1. We got to do that in all possible combinations. That's what FOIL does, right? So every possible way that you can pick something from here and here and here and multiply them together, we're going to write that down. And when we're done, we're going to add all those together. That's going to give us our expression. Still with me? Okay, how many ways can I pick something from here, here, and here so that when I multiply them, I end up with an x cubed?
One way.
There's really only one way, right? So, so that's going to be a 1. Okay, suppose I want to pick something from here, here, and here and multiply them and end up with an x squared. How many ways can I do that? Why?
So first and second, second and third, third and first.
Okay. So I could pick the x from these two, and then the 1 from the last one. That's definitely going to give me an x squared. I can pick the x from the second and third terms. That's going to give me an x squared if I put a 1 there. Or I could pick an x from the first and third terms, and a 1 from the middle one. That's going to give me an x squared. So I'm going to end up with 3x squareds when I do this. But what I actually did was I counted how many ways I can choose 2 x's from this set of 3 monomials. I said, well, I could use this and this, or I could use this and this, or I could use this and this. So this term here is really the number of ways that I can choose 2 things out of 3. Okay, exact same thought process. I want to get an x. So I'm going to pick something from here, here, and here, and when I multiply, I want a power of x to the first. So 6 is almost there.
So 9.
Colder.
And it's still 3.
It's still 3, because in order to get a power of x to the first, I have to choose one of these that I'm going to take x from, and all the others I'm going to take the 1 from. So I could say, let's take x from here only, or let's take x from here only, or let's take x from here only. And so this is the number of ways, given 3 things, that I can choose 1, which I'm going to take the x term from. And that turns out to be 3. And this x cubed term was actually the number of ways that I could pick 3 terms that I'm going to take the x from out of 3 monomials. So this is actually 3 choose 3. And if I want to get a term, a product that has no x's, I need to choose the 1 term from 3 of these monomials. So I've got to choose 3 things out of 3. Sorry, I have to choose no x terms out of the 3. So this is 3 choose 0, which is also 1. And so Pascal's triangle, right, there's 1, there's x plus 1, there's x squared plus 2x plus 1, here's x cubed plus 3x squared plus 3x plus 1. And if we write down the next row, we can hypothesize x plus 1 to the 4th is going to be x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. And that turns out to be exactly what x plus 1 to the 4th is. And so in general, if you have n of these x plus 1s multiplied together, and we're looking for the coefficient of x to the k, when we take all the pairings of a term from each monomial and multiply them together, the only time that that's going to contribute to the coefficient of x to the k is when we've taken k of these monomials and chosen to take the x term, and then we take the 1 term from the others. And each time that we do that a different way, we're going to bump up the coefficient by 1. So what's the final coefficient? It's just n choose k. So now we can write a beautiful result that mathematicians get excited about, which would be something like this: x plus 1 to the n equals the sum from, I'll probably mess this up, and choose I times x to the I. I think that's right. And that's kind of cool. And it doesn't have to be x and 1. We can generalize this. So a plus b cubed, for example, would be a cubed plus the next coefficient is 3. That's going to be a squared b. The next coefficient is 3. That's going to be ab squared. And the last coefficient is 1. And that's going to be b cubed. So we can generalize this. So it's going to be a coefficient of n choose I. And it's going to be a to the I and b to the n minus I.
No, it's
Wouldn't it be
flipped.
other way around?
The exponents would be flipped, so it would be a to the n minus I and b to the I.
And they should be the same.
Oh, yeah.
It's addition.
And because this is symmetric, so n choose I is the same as n choose n minus I, which is not obvious, but it turns out to be true.
Depends on how you order your terms.
Yeah.
Yeah.
And one more cool little thing we can do with this. Suppose we take this formula and we calculate 1 plus 1 to the n. That gives sum from I equals 0 to n of n choose I times, well, instead of x to the I, it's 1 to the I. And 1 to the I is always 1. So this is the sum from I equals 0 to n of n choose I. And that tells us that if we add up the elements of Pascal's triangle on the ith row, we should get 2 to the I. Or the nth row should give us 2 to the n, because 1 plus 1 to the n is just 2 to the n. And that's another way to see this cool little fact that if you add up across here, you get successive powers of 2. And it pops right out of the binomial theorem. So this is called the binomial theorem. The fact that this is true. All right. Good stuff. Not bad for a snowy Wednesday. So that's what most of this section 4 stuff was about. In this part was binomial theorem. And there's all kinds of good things, like proving that the size of the power set of A is 2 raised to the size of the power of A, and that will pop out as well. Or calculating strange exponents of big numbers. All right. Ready to do some Dijkstra's algorithm? All right, so you're gonna have to start by erasing the board if you don't grab one of the unerased, unwritten spots first. But let's make a fictitious graph. And I'm gonna ask you to go through this step by step, okay? So we'll do this as a group. I'll put a graph up and we'll start off by writing in tentative distances, and we'll walk through these steps together.
I was wondering if this is going to be recorded because I have to prepare this.
Wondering if what?
If this is recorded.
Oh, yeah, I am recording it.
Okay, cool.
Yeah, you'll miss this but yeah.
Okay.
I'll record what comes next. All right, I'm going to try to come up with a really good graph this time. All right, there's a really confusing graph. Ooh, sneaky technology.
Can I just take it off my ears?
You can do that, or you can do this.
Oh, that's even better.
Yeah, go to the source.
Good work. Well, I find this.
So we're trying to find shortest path from A to H. So go ahead and draw the graph, fill in the weights.
You start by going off the bridge. Oh, yeah, that's right.
Yeah, maybe. We'll see how this goes. We'll get some practice here. It'll be good. All right, everybody got a graph up? So first step is to visit A. When we visit a node, we're just going to circle it. And since this is our first node we're starting from, we're going to write down the distance next to that node and say that's a distance of 0. And then you're also going to write down a tentative distance to every other node. And what's your initial tentative distance? It's infinity, right? Because that's all we know is that we can get there in infinity or less. No guessing allowed, man. Cool. And I wouldn't circle H yet, because we're going to circle when we've actually visited a node. So, but you could underline it or something if you want to mark it as a destination. All right, good to go. So next step is to relax the nodes. So we visited node A to begin with. We want to relax the nodes that are adjacent to A that we haven't already visited. So what does relaxation mean? Basically.
Rub their shoulders.
Rub their shoulders.
So take the start way gonna be the one left on infinity. So
right.
I circled it before we did all the others.
Yeah, and don't circle anything until we're done relaxing. So relax all the adjacent nodes. So once you've relaxed all the nodes, then find the node that has the closest distance to A that you haven't already visited, and that's the node we're going to visit next. So let's see, so you relax that to a 1, and did you relax that? So you're only relaxing things adjacent to visited nodes, so only things adjacent to A. Yeah. Making progress? Cool.
Wait, and then we visit. Yeah, and now we're
You relax your nose.
And you relax which nodes? Okay, so what's the distance to B? To relax the distance. So you should start with infinities on all these. Right, that's your initial
My question is, like, after we visit this first one,
We always go to the next. You won't have to. Yeah, these are guaranteed to get you the first pass.
when we go back, right?
So instead of this being
Visit back to
Put it anyway.
We need not.
Every time you go to circle, there's a crack ball and you circle the small black one.
You have to relax it. And then.
Relax,
2, 6, 8.
D is 1. What else did you relax? Yeah, that can get you, that can be 5. Okay, so now you just relax again.
Visit B.
So you have to go down.
I'm pretty sure there is this one.
Anything you have to do.
Yeah, but when we visit, we pick the shortest
Yeah, that's
one.
what I'm saying.
So when we visit B, and then we'll actually do 5 and 1.
These are all distance nodes A that you're running in. Oh, okay. Alright, so you relax D to 1.
Oh, so the only way to get to I, it's either this way or this way, right? It's 60 degrees.
Right, so A has a distance of 0.
Oh, yeah. So now we go, now we,
So anything adjacent to A.
we're going to relax I, and then we're going to relax I.
And figure out how to relax.
Okay, now you pick the closest node to A that you have visited. E, 7 nodes circle D, so now you visit D. This tells you that D, the closest you can get from A to D is 1. So now you repeat the process, relax anything that's adjacent.
Oh, well, we don't need to
Haven't visited already.
go from here.
It's only that, that's H. Oh, yeah,
Yeah, so we're going to
That's when we're going to relax.
Alright, so now what node is closest to A? We would have to like that. Because it was low first. You haven't already visited. Yeah. So that's what these numbers are that you're writing in your distances from A.
So now we need the one that's closest to A, not the one that's closest to A.
Right.
It's higher.
So that
Yeah, because your other is 6, 8.
Do we need a certain, how do you know this?
Okay, so now we go to C, now we go to circle C.
I told you not to
Relax anything adjacent after that, then you have to.
You would relax the F and then change it to whatever, whatever would change.
Right, and that's the only thing adjacent. Okay, so now what node is closest to A?
There's a
B. Okay, circle that, just keep going. How's it coming? Good, we got there.
Yes, I think you're right, but it doesn't matter.
Actually, is that E a 6 or an H?
It's a 6. No.
Oh, okay, because you went there. Okay, good, good. Okay. So what's the process? Because it looks like you did it right. Okay, I'm going to pass out a worksheet afterward.
I have a question.
Yeah. Doesn't matter.
Right,
Make the smallest kind, usually. And if there's a unique search path, you'll end up on a unique search path. It may be there's two paths that you can see, and you'll end up on the other.
I guess it was just like weird, like coming down here and then working back.
It's reverse, that was the process. We go from 9 and we go to the, he wants to nap the
Okay, so what do we have? So now relax everything that exists that you have to write it. But now find the value of the lowest number. Those numbers are distances from A. So you can't go to the smallest number. No, you have to go backwards. Because Yep.
No, I mean, to get the notes, what you gotta do is you're gonna take, you're gonna start, follow the.
Yeah, we draw columns and stuff.
Yeah, okay.
Is this working out? As far as, okay.
Use the shortest person. And then we give so we can hop over to
Okay, good.
Yes. 1, 9, 9, because
Okay. So you relax this first, right?
I didn't remember.
So this probably should have been circled when you relaxed, when you visited it? Right, okay. And then you relax everything adjacent to here, so this should change to 8, right? Before you do anything up here or over there. And then this would have been the next thing you visited.
So we would relax this.
So, yeah, right.
And then we just stop there and then.
Say this is 8, this is 2, this was whatever it was, this is your closest, so you visit that.
We relaxed it, but
You
we never.
relax, so that would go from infinity down to 8.
Yeah, because we're like, okay, we're gonna visit this one.
Okay. So, here, well, so then you go.
No, now we're going through this way again.
And eventually it'll become
Okay,
7.
yeah. But we just smallest one.
Yeah.
Kind of jump.
Cool.
I know you just stood back there the whole time, you know, like.
Okay, cool, good. Okay, cool. Very cool. Bonk on the head.
Work today.
Actually hurts a little.
Yeah, I've been there, done that.
Yeah,
So I
yeah.
won't be able to enjoy my day.
All right, so grab a 5-minute break if you want, or I can come by and look at what you're doing, and then we'll go on from here.
I'm gonna go with my sister.
Let's go back to
At your house.
Where
Where?
you going?